There we go. Okay. So yesterday we were talking about electromagnetic waves, and we were looking at this idea of frequency and wavelength and speed of electromagnetic waves. And we said, we looked at the spectrum that all of the different types of EM waves, whether they be radio waves or gamma rays or visible light, all of those are examples of electromagnetic waves. And, you know, a real detailed discussion of electromagnetic waves is typically covered in a physics course, second semester physics course. So we're not looking into it in great detail. But let me just say a couple things about these electromagnetic waves. And again, we'll call them EM waves. Okay. First thing to say about them is that they are oscillating. They're disturbances in space. So they have some sort of repeating pattern to them. The name electro and magnetic, it's essentially two words put together. What that's essentially saying is that they create what's called an electric field. And they also create what's called a magnetic field around them. Okay, so as they move through space, right? So they're moving through space. So imagine a light source. You've got like a light bulb or a star or something like that. Essentially what it's doing is it's emitting these electromagnetic waves, and they're all moving in different directions, right? All around it. As they move, they oscillate, right? So they're vibrating in some way. They're changing their height up and down, up and down, up and down. And around them, they create electric fields and they create magnetic fields. So that's the sort of the name of it, electromagnetic wave. That's why we call them that. Okay. One thing to say about them is it doesn't matter which type of electromagnetic wave we're talking about, whether it be a radio wave, whether it be a microwave, whether it be infrared, whether it be visible, ultraviolet. These are the general categories of these waves. X-rays, and then gamma rays. Doesn't matter which one, they all have the same speed in a vacuum. The speed of these waves in a vacuum is c, the symbol for it is c, and it's equal to 2.9979 times 10 to the 8th meters per second, which is enormously fast, okay? I mean, at least relative to the sorts of speeds that we're used to dealing with, okay? And so this speed, you treat it as a constant, right?
Be quiet, Belle.
And the constant is equal to the wavelength times the frequency. Okay, so this is your wavelength. And then you're multiplying it by the frequency of the wave. So those are both, actually all three of them are properties of the wave. So there's a wavelength, which is a measure of essentially how long it is. So it's the length of one complete cycle. So it's a distance, right? So this is a distance.
Hello.
And then the frequency is the number of cycles per second. So imagine this thing vibrating, oscillating. How many complete cycles of vibration does it undergo every second? Okay, so there is an example in ALEKS that you need to do, which is getting into the issue of units and how to think about these electromagnetic waves. So let me show you this example. What they do in this problem is they tell you that you're going to break a chemical bond. Using electromagnetic waves. Okay, so let's talk a little bit about how that happens. I'm going to represent the chemical bond. Let's take a simple molecule, hydrogen, H2. So H2, hydrogen, has 2 atoms, right? There's 2 hydrogen atoms. And if you think about it, hydrogen is very simple, right? So it's just got a proton at the center, right? The nucleus of the hydrogen atom just has 1 proton. And then it has an electron outside of that proton. Okay, so there's a little electron here. And then the other atom would be the same thing. But what I'm going to do is I'm going to represent the bond in this molecule in the following way. So there's the second atom, right? There's the second hydrogen atom. There's the first one. Both of them have a nucleus. I'm going to represent the electron that's in that second hydrogen atom next to the one that's in the first atom. So now these 2 electrons are together. This is a little bit of foreshadowing. We'll get into this in chapter 8. But essentially, we can think of a chemical bond as having these electrons. Each atom is using one of its electrons to form a pair of electrons. And we're going to call that pair of electrons, we're going to call that a chemical bond. Okay. Now, in a sense, this problem that you're going to do here in chapter 6 is a little bit of foreshadowing what we're going to do in chapter 8. So essentially the problem says, look, it takes 498 kilojoules per mole to break a chemical bond in oxygen. Okay. Calculate the maximum, let me see, make sure I get this wording right. The maximum wavelength of light okay, let me come over here. Sorry. Maximum wavelength of light to break this bond. Okay. Now, in order to answer this, we need one more equation. So let me write the equation we had here. We had C equals lambda times F, right? So speed of light, which is a constant, is equal to the wavelength of the wave, the light, times its frequency. Okay. But now we're talking about energy here. See how there's energy in here? Those are energy units, kilojoules, right? So now we need another relationship. We need an energy relationship. And so I'm going to give it to you right now. E, the energy of electromagnetic waves, is equal to H, which is another constant, times F, which is the frequency. So what this equation says is the energy of these electromagnetic waves is equal to a constant called Planck's constant times the frequency of the wave. Okay. Now, what essentially was found in the same time period that we're talking about, which is the early part of the 20th century, so 1905, 1910, 1915, that time period, was that if you actually decompose light, so when we think about a light bulb, right, so this light bulb is producing light. If you study the properties of that light, what you'll find is that it's actually comprised of little particles, or I shouldn't say little particles, it's comprised of particles. So when light moves through space, it's actually individual particles moving through space. And we call those particles photons. Okay. And each of those photons has an energy, right? So think about it. Something's moving through space, it has energy, right? So these photons have energy. And it may not be obvious, but it turns out the energy of a photon really all it matters is its frequency. The energy of a photon is just equal to h times the frequency. So you can figure out the energy of one photon. All you need to do is measure its frequency, which is pretty easy to do. And then you just need to know what Planck's constant is. So Planck's constant is known. So let me give you the value here. H is a really, really small number, 6.626 times 10 to the negative 34 joules. So those are energy units multiplied by seconds. So it's sort of odd units. It's not joules per second, it's joules times seconds. And this is a fundamental constant of nature. Okay, so keep in mind we have two constants that you have to remember. The first one is Planck's constant, and then the second one is the speed of light in a vacuum. This is meters divided by seconds, right? So those are our two constants that you use for this discussion. Okay, so here's the logic then. They tell us how much energy it takes to break a chemical bond in oxygen. Okay, they call it a double bond. That's perfectly fine. You don't have to worry about that yet. We'll get to that in chapter 8. That's the fun part of this course is chapter 8. But for right now, essentially what they're saying is one of these photons is coming through space and it's interacting in some way with the molecule. Now this is hydrogen I've drawn here, but it works the same way with oxygen. And it essentially puts enough energy in. Let me show it over here. It puts enough energy in, because a photon has energy, to break that bond. And essentially the two atoms then separate with their electrons. Okay, so this is called bond breaking, and we'll talk more about it in chapter 8, but they wanted to put this problem in here so that you could go through the dimensional analysis. So here's all we really need. We need these two equations. We need the values of these two constants, and then we need the number that they gave us, 498 kilojoules per mole. Okay, so I'm going to go ahead and just write all those numbers down, all those equations on a separate sheet here, and then we'll do this problem. So the energy of a photon is hf. The speed of a photon is lambda times f. And then we have these constants. H is equal to 6.626 times 10 to the negative 34 joule seconds. C is equal to 2.9979 times 10 to the 8th meters per second. And then the energy of the bond is 498 kilojoules per mole. Okay, so they throw a lot at you in this problem. There's a lot of conversions you have to do in this problem. So let me just sort of draw out a little flow chart for how you approach this. We are essentially asked for the wavelength. So they ask us to find the maximum wavelength that can break the bond. Okay, so here's how I'm going to approach this. The wavelength is lambda. So how do we find lambda? Lambda is equal to C divided by F. You just divide both sides by F, right? So if you divide this side by F and you divide this side by F, you get lambda, okay? So in order to find lambda, in order to find this maximum wavelength, we've got to have the speed of light. Okay, well, we've got that. That's easy enough. That's just a constant. And then we have to divide that by F. But how are we going to find F? Well, all we know is energy of the chemical bond. So that's E, right? That's E right there. So now what I'm going to do is I'm going to say, okay, well, what is F? F is E divided by H. So I'm going to write this in as E divided by H, right? So and we know what H is, right? So let me go ahead and put in H. H is 6.626 times 10 to the minus 34 joule seconds. I'll put that in parentheses just so you can see it's E divided by H. Okay, so we're almost there. We just got to find E. Now just be careful. You can't put in 498. That doesn't work. And the reason that doesn't work is, first of all, it's not in joules. The value of H is in joules seconds, not kilojoules seconds. So this has to be in joules. So how do we get it to joules? What you do is you say it's 1,000 joules per kilojoule, right? So your kilojoules will cancel and you get 498,000 joules per mole. So we're almost there. But then there's this issue of the mole. The problem is, what is this mole? So the issue here is that when we talk about how strong a bond is, this is a measure of how strong the bond is. It's in energy units. It's typically given in per mole. And the reason for that is that if you do it just per one molecule, it's such a small number that it's like not easy to use. So 498, for example, often we use prefixes and we use units just to make things like easy numbers. 498 is easier than 498,000. If you were to do it for one molecule, it would be like 10 to the minus 18 joules. And that's such a small value that we don't put it in those units. So the typical units are per mole of molecules. So really all we want to do is just figure out how much is one molecule. So it's 498,000 joules per mole. Now, what does that really mean? What that means is, we did this back in chapter 3, a mole is 6.022 times 10 to the 23rd molecules, right? But we don't want for every 6.022 times 10 to the 23rd molecules. We just want it for one molecule. We just want one photon of energy, okay? So how do we do with that? Well, the way I'm going to do it is I'm going to say 498,000 joules per mole, so joules per 1 mole, and then I'm going to say 1 mole is 6.022 times 10 to the 23rd. And then the moles will cancel, and that will give us for one molecule, okay? So 498,000 divided by 6.022 times 10 to the 23rd. And again, you get this really small number. It's 8.270 times 10 to the minus 19 joules. Okay, so that's just for one molecule. We don't want to break a mole of oxygen. We just want to do one. So the issue here is that when you look these values up, they're per mole, but we want it per molecule. Okay, so you got to do that conversion. So now we've got our energy. We can put that right in there. Now the logic of this is, what photon can break the bond? So they give us the energy of the bond, and then we're going to say, okay, the photon has to have that amount of energy in order to break the bond. Okay, so let's go ahead and put it in there. Wavelength would be 2.9979 times 10 to the 8th meters per second. So there's your C. We're dividing that by E over H. E is 8.270 times 10 to the minus 19 joules. And then we're going to divide that by H. 6.626 times 10 to the minus 34 joule seconds. And so now, you know, be careful with this because you've got all these powers of 10. And so it's very easy to get it all kind of mixed up. But let's go through the dimensional analysis. We have, it's a little tricky. It's hard to see this, but this one's easy. Joules over joules, that cancels. That's very easy. This is really meters over seconds divided by 1 over seconds. So the seconds cancel too. So you're just left with meters. So that's easy. Now you just have to do the scientific notation and all of that. So what I'm going to do is I'm just going to go ahead and write, 9979 times 10 to the 8th. And then I'm going to do what's in the denominator, 8.27 times 10 to the minus 19 divided by 6.626 times 10 to the minus 34. And you get 1 0.248 times 10 to the 15. Okay. Now I'm going to go ahead and do the division. So 2.9979 times 10 to the 8th divided by 1.248 times 10 to the 15. And what you get is 2.4. Actually, I should put one more sig fig in there. So let me multiply that by 10. 2.40 times 10 to the minus 3 and 4 is 7 meters. And there you go. There's your answer. Okay. So that is a unit, right? Wavelength, it should be in meters or centimeters or micrometers. It should be in length units. So let's go back. Let's review this because there's a lot of steps in here. It's not as hard as it looks. What they do is they give us the energy of the bond. What you do is you assume the energy of the bond is equal to the energy of this photon that's going to break the bond, right? So think of it this way. Like if you have a wall and it takes a certain amount of energy to break through that wall, you put in that amount of energy and you break the wall, right? So the energy of the impact has got to be equal to the energy holding the wall together. If they match each other, the wall will now break. So what you're doing is you're saying, we know the energy of the bond. How much energy does the photon need to break the bond? Well, it needs the same amount of energy, 498. But they put it in funny units. They don't put it in joules. They put it in kilojoules per mole. So you have to go through a little conversion. You have to go from kilojoules per mole into just joules of one molecule. So the way you do that is multiply by 1,000 to get it into joules, and then divide by Avogadro's number to get it for one molecule or one photon, as opposed to a mole of them, okay? And then once you've got that energy, then you can go through these two equations here. Those are the two that you'll use for these types of problems. The energy is equal to HF. So in order to solve this problem, you need to know what F is, right? So to find out what F is, you use E and H. E and H will give you F, right? So that's what we did here. We said E and H gave us F, which is right here. And then the question was, what's wavelength? Then you use this one down here. C and lambda and F are all related. So if you want to find lambda, you take C over F, okay? C over F. And there you go. All right, so E over H is giving us F. Lambda is C over F, so E over H would be your F there. And then it just all works out. So that particular problem is called interconverting wavelength, frequency, and photon energy. So you're going to see a couple of different types of problems there. Sometimes they just give you wavelength and frequency. Sometimes they give you wavelength, frequency, and energy. Okay. Oops. Okay, so speed equals wavelength times frequency, and then energy is equal to Planck's constant times frequency. So those are the two equations you can use. If they give you the wavelength and ask for the frequency, you don't need the second one, you just need the first one. But if they talk about energy, you're probably going to need both of these equations. Okay, so let me just show you real quick, just a little picture of the idea here. You've got this oxygen molecule. Now they actually tell you it's a double bond, so I'll represent it using their sort of notation here. So there's your oxygen double bond. Picture this in the following way. Don't worry about sizes. The sizes are not real, but I'm just drawing a little diagram just so you can conceptually understand what's happening. You've got this photon, and then you've got this molecule. The atoms in the molecule are stuck together, right? So essentially what we're claiming is the photon is going to come in here and it's going to smack into that chemical bond. And as it smacks into the chemical bond, the energy of that photon which depends on its frequency, is going to be transferred into the molecule. And if it has enough energy, it'll break the molecule into two. So you'll have one oxygen atom flying off this way, one oxygen atom flying off that way. The energy of the photon is now converted essentially into kinetic energy, right? Because these atoms are now flying apart. So now they have kinetic energy. So we haven't created any energy or destroyed any energy. The photon no longer exists after this collision. It's gone. But its energy has been transferred into these atoms through kinetic energy. Okay, it's kind of cool. It's a phenomenal type of experience. Okay, so that's how you're looking at it. So then you're just using these two equations and doing unit conversions in order to solve the problem. Okay, now that kind of leads us, in a sense, it's a little bit ahead of the game by putting that into section 6, because really that question, in a sense, is a chapter 7 or a chapter 8 problem, but that's okay. We'll go ahead and take a look at this stuff anyways. Okay, so the next issue then is, how do we deal with this idea of the electrons and the structure of the atom? So what we're going to do now is we're going to look at section 6.3, which is called the Bohr model. And this is going to get a little bit into the physics of the structure of the atom. And so we'll start with the Bohr model. So to do the Bohr model, let's begin with a simpler model, which is called the planetary model. So we'll start with that one, sometimes referred to as the nuclear model. Okay. There's all kinds of history behind this, but we're not going to go through that. So the planetary or the nuclear model says essentially this. And we're going to use hydrogen as our example. The nucleus has a hydrogen, the nucleus of the hydrogen atom has a proton, and the proton is positively charged. Outside of the nucleus is an electron, and the electron is in motion around the nucleus. Let's assume it's circular, okay? So here's our negatively charged electron. And what holds those two particles together is electrostatic attraction, right? Opposite charges attract, so they're attracted to each other. Okay, so there's a force of attraction or an energy of attraction due to those opposite charges. Okay, each of those particles is creating an electric field. Those electric fields interact with each other and you have an attractive energy or an attractive force. Okay, but the electron essentially is in motion, right? It's revolving, it's orbiting, right? Orbiting the proton. Now, why is it that way? Why does the electron orbit the proton? Why not the other way around? Why doesn't the proton orbit the electron? In general, it has to do with mass, right? Remember, the electron has a really small mass, 9.109 times 10 to the minus 31 kilograms, whereas the proton is 1.67 times minus 27 kilograms. So the proton is thousands of times heavier than the electron. So the lighter particle orbits the heavier particle, right? Just like the sun doesn't orbit the Earth because the sun is so much more massive than the Earth. The Earth orbits the sun. But in fact, 1,000 times heavier is really not as big as the difference between the Earth and the sun. The sun is trillions of times heavier than the Earth. So for that reason, or billions, it's billions of times heavier. So for that reason, the Earth goes around the sun. But 1,000 times, they actually go around each other a little bit. So if you actually look at the orbit, the proton is actually orbiting the electron a little bit too, okay? So now that's our model, right? The Bohr model, what it does is it extends that model to say a couple of different things. What it says is, again, let's keep the proton at the center, is that the electron actually has multiple orbits. Let me go ahead and redraw that circle, that orbit. There are more than one orbits for the electron. So there's one. Here's a second. Here's a third. Again, let's just assume they're circular. Okay, now just for simple, I'm just drawing a really crude picture here, but we can say the electron, I'm gonna number these orbits. This one is n equals 1, n equals 2, n equals 3, and then n equals 4. And we don't have to stop at 4. We could continue to 5 and 6 and 7, as far as you want to go out there, okay? But there are these orbits that the electron occupies, okay? Now, what Bohr said was that what essentially happens is, imagine that you have an electron. Go ahead, sorry. There we go. Imagine that you have this electron in the first orbit, n equals 1. How does the electron get up to upper orbits, to the second level or the third level or the fourth level? Okay, so we call these levels states. So these levels, n equals 1 or 2 or 3 or 4 or 5 or 6 or 7, we call them states, right? Or we call them orbits. So there's different names for this: level, orbit, state, okay? It can undergo, the electron can undergo a transition between states. And we can represent this in the following way. Let's say the electron's in the first level. We'll just say n equals 1, okay? It can undergo a transition to n equals 2, right? It could go from 1 to 2. So how would I represent that? I'm going to represent it with an arrow that looks like this. Okay, that's how we would represent the electron going from n equals 1 to n equals 2. Now remember, hydrogen only has 1 electron, so it can't be in both places at the same time. It can't be in, we're just dealing with 1 electron, okay? So that's called a transition. And the question is, how does the electron get up there? Well, there's a couple of different ways. One would be if you could somehow transfer enough kinetic energy into the electron to knock it up there, right? So like, electron's a particle, right? If you hit it with enough energy, you could knock it up to the second level. That'd be one way. Another way, however, which is going to lead us into an interesting discussion here, is that a photon has energy. If the photon has the right amount of energy, then that's another way to get the electron from the first state to the second. And this is called absorption. The electron absorbs a photon, taking its energy, taking the photon's energy. Okay? If the energy of the photon, all right, E photon, is equal to the difference in energy, meaning the difference in energy between n equals 1, and n equals 2, then the electron can jump to the second level. Okay, now that's the important point here. If this photon, so let me show a little picture. Imagine you got this photon here. This photon is moving towards the atom. So it comes through these orbits, interacts with the electrons. So somehow there's an interaction between that photon and the electron. If the energy of that photon is equal to the difference in energy, I'm going to write E2 minus E1. We'll call that delta E. So if it's equal to the difference in those two energies, then what will happen is the photon gets absorbed by the electron, and the electron is now promoted to the second level. Okay, So the photon has now been absorbed. Okay, it just gets absorbed by the electron. So where does it go? It doesn't go anywhere. It's just actually in, it's part of the electron now. And so now the electron has more energy. Oops, wow, what happened there? Okay, let me go back. There we go. The electron now has more energy. It has the energy that it had when it was in the first level, but now it has an additional amount of energy that came in from the photon. That's called absorption. And in theory, an electron could go from 1 to 2, or it could go from, I see what's going on. It could go from 2 to 4, right? That would be possible as long as the energy of that photon is equal to the difference in those two energies. That's a matching principle, they call that. Okay, so if the energy of the photon, remember we said that's HF, right? H times F, that's the energy of a photon. If the energy of the photon matches delta E, then it will be absorbed. And promote to make it go higher, the electron to a higher level. And then remember, there's 3 different words: level, orbit, or state. State is a very common word that we use for that, okay? So now, what about energy? So what I'm going to do is I'm going to show you what's called an energy level diagram. We did this a little bit when we talked about enthalpy in chapter 5, but let me show you where it's really applicable. This is called an energy level diagram. What I'm doing, this is E for energy on the y-axis, is I'm showing you how much energy the electron has in each level, in each state. So this is n equals 1. This is called the ground state because it's on the ground. So you can't have n equals 0. N has to start at 1. Okay. Then you have n equals 2. This is called an excited state. It's a cool name, excited state. If the electron is in n equals 2 or above, these are called excited states, meaning they have more energy than the ground state. They're excited. Okay. So this is n equals 3, n equals 4, n equals 5. Notice how they're getting closer and closer to each other. This is called convergence. It's a concept you see in mathematics classes, right? Things can converge, right? So it's converging to some amount, n equals 6, and it actually converges at what we would call n equals infinity, or at least n approaches infinity. Let's use that, okay? And this is called the ionization state. Okay, the ionization state is the state where n is so large, the electron is no longer part of the atom. It's ionized. So now the atom is an ion because the electron is gone. So you start at the bottom, n equals 1, that's called the ground state. Every level above, that's an excited state. And then once n is large enough, then we call that the ionization state. And the electron is no longer part of the atom. So remember, the photon is being absorbed by the atom, by the electron. So actually, let me show you a point here. Suppose the electron's here, and I'm going to represent the electron using an arrow. We'll talk more about that in a later chapter, or later in this chapter. So I'm going to use this arrow to represent the electron. You'll notice that we use arrows a lot for different contexts. In this context, the arrow just means an electron in the atom. So what happens if this photon comes in? So you got this photon moving in, and it doesn't quite have enough energy between 1 and 2. Suppose it has enough energy to where the electron could get up to here, right? So it's got enough energy to get it to, 1.9 or something like that, but not quite 2. what we would claim happens is the photon just wouldn't get absorbed. It will just go right on through. So only one energy works to get it from 1 to 2. It's the energy of the photon has to match exactly the energy between 2 and 1. And again, that's called energy matching. Right? It's got to match it perfectly. So in order for the photon to get absorbed, it's got to equal exactly that delta E, which is E2 minus E1. Okay. Now there could be another photon between 1 and 3, right? So it could also do that. It could go from 1 to 3. That's possible. But that energy, that photon would have to have even more energy. It would have to have even more energy than the first one, right? It'd have to have, you know, delta E here would be E3 minus E1. It would have to be E3 minus E1. Or suppose the electron's already in the second level and you want to go up to the fourth level. Okay, well, that's perfectly fine. But now delta E would be E4 minus E2. And that happens. That happens in the hydrogen atom, okay? Now, this also is useful for molecules, but we're just doing it in the context of a hydrogen atom for right now, because the hydrogen is simple. So we can do the calculations more easily than we can with other types of species, okay? So energy matching, this is called absorption, or absorption is uphill. You're taking the electron and going up to a higher level as absorption. But guess what? The opposite can happen too. So it turns out that if you already have the electron in a higher level, so let's say it's in the second level. So it's up here. So it's already excited, right? This electron is excited because it's in the second level. It's not in the first level, okay? It turns out spontaneously, that means on its own. It's a really cool science where you look into these things. The electron can jump back down to the first level on its own. It doesn't require any pushing of it to happen. It'll just on its own jump back down. It does it statistically. So there's a transition, right? That's a transition. A transition is going from one state to another. So let's say n equals 2. So the electron starts there and it goes to n equals 1. That's a transition, right? So it's going to jump back down to here. Okay, well, what happens in that case is the opposite process occurs. In absorption, the electron is promoted to a higher level, right? So let me show you in terms of an energy level diagram. So if the electron is going from 1 to 2, that's absorption, right? It's absorbing the energy of a photon. Absorption of a photon. So you need that photon for that to happen. But what happens if it does the opposite of that? What if the electron is in the second level and it goes down to the first level? The opposite occurs. You get called emission of a photon. The photon comes into existence. It is created in this process. So this is a fascinating aspect of how the universe operates. Photons are created when electrons jump from one level down to another, downhill. And we call this emission of a photon. So the photon will just fly right out of the atom. It'll take its energy right out of the atom, and the energy is equal to the difference between those two states. So the electron has lost energy. The photon now exists. It takes and carries as a packet. It carries a packet of energy away from the atom. So this allows atoms, in a sense, to communicate with each other. An atom can release a photon. That photon could fly over to another atom, get absorbed by that atom, and now those two atoms have essentially communicated energy between the two of them, right? So this is called emission, okay? You can think of this as exothermic, right? Exothermic is where you release energy. So this is analogous, right? It's an exothermic process in the sense that it's releasing energy. Now it's really exergonic, it's not releasing heat, right? Exothermic means you're releasing heat. This is not heat, this is radiative transfer. It's radiation that you're producing. But it's also called exergonic, which means it's releasing energy from it. But it's analogous to exothermic, okay? All right, so we have emission, we have absorption. Can you do calculations with it? Absolutely, there's calculations that can be done with this, but just remember that delta E is, I'm going to write it this way, E final minus E initial. And this is the energy of the atom, in this case, hydrogen. The calculations we're doing in this section are just for hydrogen. We're not doing them for any other elements, okay? And then remember that you've got this E of the photon, which is HF, but it can also be written in terms of lambda. It can also be written as HC over lambda, right? And the reason that that can be done is that C equals lambda times F. So if you just substitute, F equals C over lambda, you can put the C over lambda in right here, and you got HC over lambda, and that will work for you too. So remember, it's matching, right? So the energy of the photon that's either released is equal to the delta E of the atom, or the energy of the photon that gets absorbed is equal to delta E, E final minus E initial of the atom, okay? Absorption, emission. Emission is when the electron goes downhill. Absorption is when the electron goes uphill. It's kind of cool. So let's take a look here. Okay, so let me show you an example. Okay, so we're going to calculate the wavelength of the wavelength of a line in the spectrum of hydrogen. Okay, so before I actually do a problem in this, let me show you a little bit about this idea of lines. Okay, what happens is if you take a hydrogen atom, and remember you've got these different orbits or states or levels, whatever you want to call them. Okay. The electron, suppose the electron goes from, let's call this 1, 2, 3, 4, let's do 5, 6. Okay. Suppose the electron's in the 6th level and it jumps down to the 2nd level right here, n equals 2. Okay. So that would be n equals 6 goes to n equals 2. Now remember, it's going downhill, right? So it's going to emit a photon. Right, so there's going to be a photon emitted. And the energy of that photon is going to be equal to delta E, energy of the 2nd level minus the energy of the 6th level, right? E final minus the initial. But suppose the electron's in the 5th level and it goes down to the 2nd level. Well, that would give you 5 going down to 2. And again, it's going to emit a photon. That's fine. It emits a photon. But it's going to have a different energy, right? It'll have a different energy if it's starting in the 5th level. Suppose it starts in the 4th level and goes down to 2. So it starts here and it goes down to 2. So it's starting at a different level, but it's always ending at the same. Again, you're going to get a different level, a different energy, right? They're all going to have different energies. And then the last one would be 3 goes to 2. Okay, this will also emit a photon. So what happens is you end up with an interesting pattern. And the pattern I'm going to show you is this. It turns out all of these are in the visible spectrum of light. Okay, so they're not ultraviolet, they're not X-rays, they're not radio waves. It turns out they're visible. So that means you can see the photons. The photons, you can observe them with your eyes, you can measure them with instruments very easily. Okay, so remember, we have this relationship, E of a photon is equal to HF, but that's also equal to HC over lambda. So there's a relationship between lambda and the energy of a photon. Now it's an inverse relationship, right? This is in the denominator, lambda is in the denominator. So as this gets larger, energy gets smaller. But what I want to do is I want to just show you what you get. You get 4 different colors. Okay. You get 1, 2, 3, 4 different colors, and each of those are called a line. So I'm going to do the visible spectrum. The visible spectrum is 400 nanometers to 700 nanometers, and this is wavelength. Okay, so that's visible light. And as you get close to 700, like 640 to 700, that's what we would call red. So any photon that comes into your eye that's between 640 and 700, you would perceive that as red. So what's happening is photons that are bouncing off of things that are red, they look red to us. Those are the photons that are bouncing into your eye are between 640 and 700 nanometers. All the way over here at 400 is what we call violet. So you know what violet is, like a purple color, right? And then it's blue, and then it's green, and then it's yellow, and then it's orange, and then Roy G. Biv. Okay, I didn't put indigo in here, but indigo is right in here between blue and violet. So here's what happens. You get one of these photons, this one right here. It turns out that's right around here, around 410 nanometers. And it appears purple. It's violet. Okay. And then you get another one that's at 434. And that's kind of starting to look a little bit like blue. And then you get another one out here that's about 486. And that one appears green. And then there's another one out here at about 656. And that one appears red. So you get, violet, blue, green, and red. This is for hydrogen. And that's if the electron goes from 6 to 2, 5 to 2, 4 to 2. So imagine the electrons just kind of bouncing back and forth. Wherever it starts, that's going to determine the color. So the pattern, we're going to do the calculation. If not today, then we'll do it tomorrow, I guess. The pattern is essentially this. When the electron goes from the 6th level to the 2nd level, that's the 410 nanometers. Okay. When it goes from the 5th level down to the 2nd level, that's a 434. And then when it goes from the 4th level down to the 2nd level, that's 486. And then when it goes from the 3rd level to the 2nd level, that's 656. Okay. So my point of this is the following. Each of these lines that are seen, that are observed, correspond to one of these transitions. And so if the final value of n is 2, and the initial value is above 2, 3, 4, 5, 6, 7, 8, 9, then you essentially get light that's visible. If the final value is a 1, so 2 to 1, 3 to 1, 4 to 1, 5 to 1, it turns out we can't see that with our eyes. The energy of those photons are in the ultraviolet. And if it's, the final value is a 3, so 4 to 3, 5 to 3, 6 to 3, 7 to 3, we can't see those either because they're in the infrared. They're just not in the wavelength range of our eyes. Okay, so we're really, for hydrogen, we're only able to look at these particular things, but we have instruments that can look at ultraviolet. We have instruments that can look at infrared. But here's what I want to show you, kind of get you into this calculation. The calculation you can use is this. The energy of the electron is equal to negative R divided by n squared, where R is called the Rydberg constant, Okay, and it has a value. The Rydberg constant is a small number, and it's available. I would get it out of Alex. Don't get it out of your textbook because they use a slightly different value in your textbook. It's 2.17987 times 10 to the minus 18 joules. They're pretty close in your book. They use 2.18. They just round it to 3 sig figs, but in the Alex, you see it with more sig figs. Okay, so this is the energy of the electron in the hydrogen atom. So what you can do is you can say this. Suppose we have a problem where the electron is in n equals 6 and absorbs a photon. To go to n equals 11. Okay, calculate the energy difference between these two levels. Okay, so imagine it this way. So they pick some big numbers, 6 to 11. That's pretty amazing, 6 to 11. So let me do this. I'm going to start at 6. We'll just ignore 1 through 5. 7, 8, 9, 10, and then 11. Okay, and remember this is an energy level diagram, so this is E. So what they're saying is, suppose the electron goes from the 6th level up to the 11th level, calculate delta E. So it would be the energy at the 11th level minus the energy of the 6th level, right? Final minus initial. Okay, so all you got to do is just calculate E11 and then E6 and then find delta E from that. Right? The 11th level minus the 6th level. Okay. Tomorrow we'll convert it to wavelength. We'll continue working on it, but I want to show you how to get to this far. So here's how you do it. You say, okay, well, let's do E11 first. So we're just going to put 11 in here for N. So it would be minus R. So minus this number right here. Divided by 11 squared. Right? So you do N squared, not N, but N squared. 11 squared is what 121, right? 11 squared is 121. So now you're going to calculate that. So you'll get a negative number because of that negative in front of there. So 2.17987 times 10 to the minus 18 divided by 11 squared, which is 121. So you get negative 1.80155 times 10 to the minus 20 joules, okay? So now keep all those sig figs in there because the quantum numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, those states, those are exact values. You can't have 11.01, so 11 is an exact number. So use the sig figs that you have in your constant here. Now we do E6, which would be E minus 2.17987 times 10 to the minus 18 joules divided by 6 squared, which is 36, right? Okay, so let me erase this down here. So let's do that calculation. So 2.17987 times 10 to the minus 18 divided by 36, and you get negative 6.05519. What's that got? 1, 2, 3, 4, 5, 6. And we had 1, 2, 3, 4, 5, 6. Okay, so 94 times 10 to the minus 20 joules. Okay, so now you just do E11 minus E6. And you can see that this would be absorption, right? So you have minus 1.8 0.0155 minus a minus. So that's the same as a plus, right? Minus a minus is plus. So that'd be the same as plus 6.055194. The whole thing is times 10 to the minus 20 joules. Okay, right? Because if they're both times 10 to the minus 20, you can just factor out the 10 to the minus 20. So now you have negative 1.80155. So 1.80155 negative plus 6.055194, and you get 4.25365 times 10 to the minus 20 joules. And that'd be your answer right there. Okay. A lot of numbers playing there. That's your delta E. Okay. So, you know, I did two little tricks there. I said, look, I'm subtracting a negative number. Both of them are negative. So the second one that you subtract, you're subtracting a negative. So that makes it plus. Just put those two numbers together. The second number was larger than the first number. Since it was larger, you're going to get a positive answer. If you take a negative number and you add a positive number, so negative number plus a positive number, if the positive is bigger than the negative, you're going to get a positive result. And then they're both times 10 to the minus 20. So I just factored out the 10 to the minus 20. So that essentially gives you delta E, right? That's the energy difference between 6 and 11. Okay. Now, if you get a positive value, that's absorption. Absorption is positive. Okay. Why? Because it's endothermic, right? It's endergonic. You're going from a lower level to a higher level. That takes energy. So you got to put the energy in. So that's endo, right? So positive. Okay. Now, what we'll do tomorrow is we'll finish this problem, but we'll look at it from the perspective of wavelength. In these questions, they ask you to figure out the wavelength. So we've got our energy. So figuring out the wavelength of the photon that got absorbed to do this, not a problem. We'll just use E equals hc over lambda, and then we'll have our wavelength. Okay, but we'll do that tomorrow. Tomorrow's Thursday. That's the last day of the week, and we'll get through that. And then let's see, we'll do that problem, and then we'll start looking a little bit at chapter 6, which is wave properties of matter. So we'll look at the de Broglie wavelength, which is a good one, and we can get through that tomorrow, and that'll be a good start for you guys on chapter 6. That'll get us about halfway through 6. And then next week, we'll keep working on 6. We'll grind through it. It's a pretty long chapter. There's a lot of stuff in this one. And it's actually looking through it. Well, it's 18 topics, but it's some pretty intense stuff. Okay. So have a great day, guys. I am around. So if you have any questions, reach out to me. And I hope everything's well, and take care.
Thank you, Professor.
Oh, by the way, let me make one mention. So if you know anybody that's planning on taking Chem 11 this summer, so that wouldn't be you because you're already taking, but if you have any friends that are taking it, you might want to let them know that there's going to be one section that we're teaching. We hope to teach it, that is what they call high flex, which means that if you want to, you can come into the campus to take the labs. So we'll do the labs on campus. If you don't, then we'll have sections where you don't have to come in. And it looks like it's just going to be 1 day a week. So 1 day a week, you'll be able to come onto campus. So we're going to kind of pilot that this summer. And so if you know anybody, if you have any friends that are like a semester behind you and they're planning on taking Chem 11 this summer and they're interested in that coming on campus, let me know. It looks like what we're going to do in the fall at Kingsborough is have what are primarily called hybrid courses. So the laboratories will be on campus, and then the lectures will probably be on Zoom. So that's what we're shooting for. We don't have final word on that, but I'm going to try to pilot this sort of high flex thing this summer. Okay. So just a little announcement if you have any friends. So take care, everybody.
Thank you, Professor.
Bye-bye.